In this problem, a 5-gram bullet traveling at 300 meters per second strikes and is embedded in a 500-gram stationary target. The bullet and the target move across a level frictionless table and it strikes a spring, and we have to calculate the maximum distance the spring can be compressed. I'm going to start by visualizing the problem. Just keep in your mind, this is a multi-stage problem. Why? Because there's a part of the motion we can use conservation of linear momentum, and for the next part of the motion, we can use conservation of energy. So I'm going to visualize the problem. Initially, the bullet is moving at 300 meters per second and it has a mass of 5 grams. And the target is at rest. So the speed of the target would be just 0. And after the collision, they move as one system, which means this is a perfectly inelastic collision. The target and the bullet will have a common speed after the collision, and for that part of the motion we can use conservation of linear momentum because there's no external force acting in the system. I'm going to use Vs to denote the speed of the system after the collision. The reason is this is not the final speed of the system, so I just don't want to confuse you guys. So for that reason, I'm just using Vs, and then the system has the common speed. The mass is 505 grams. And for the second part of the motion, we cannot use conservation of linear momentum. Why? Because there's an external force acting in the system. What is this external force? What is the reason? Because if you look at the spring, there's a fixed end to the spring, and from that fixed end, there's an external force acting in the system. So this is the initial situation when the bullet is embedded into the block. They have a common speed. We can calculate it from the previous step. And the spring is neither stretched nor compressed initially. And then the system is going to move on a frictionless surface, and it's going to compress the spring to a maximum amount, which means the speed of the system at the final stage would be 0, and we have to calculate the compression. X is the compression, by how much does the spring compress. Okay, so again, keep in your mind, we cannot use conservation of momentum because there's a net external force from the fixed end of the spring. The spring constant is 1000 newtons per meter. Okay, so let's see the applicable concepts. We can easily see it from the visualization. We are going to use conservation of linear momentum and conservation of energy. So have we specified the coordinate system? Yes, we have specified the coordinates. I have taken right as positive. I just wanted to mention this. I have already shown the height is equal to 0 level on my conservation of energy diagram, and we are trying to calculate x, and it's measured in meters. The unit positive. So first equation, the conservation of linear momentum equation. By now, pretty sure you guys are familiar with this equation. And the second equation is our 7-term conservation of energy equation. You used this in the previous chapter. So I'm going to write all the terms, not only the gravitational potential energy, but also the spring potential energy here. Okay. So now let's execute the plan. Just keep in your mind, again, this is a perfectly elastic collision because the two objects collide and move as one system. So we expect to have a common speed. We just use Vs to denote the speed of the system after the collision. And mass of the first object times the velocity plus mass of the second object times the velocity is equal to combined mass of the system times the velocity. And we know the velocity of the bullet is 300, velocity of the stationary object just 0, and then 505 grams times the speed. So you can solve for the velocity of the system after the collision. That would be equal to 2.97 meters per second. So we are not done yet. This is the first stage of our multi-stage problem. Let's do the second step now. In the second step, we are going to use conservation of energy. We cannot use conservation of momentum here because there's an external force acting on the system from the fixed end of the spring. And so these are all the terms in your conservation of energy equation. I'm going to cross out the unwanted terms. Gravitational potential energy is 0, and the initial spring potential energy is 0, and then work non-conservative is 0. Why? Because the object is moving on a horizontal level, there's no change in height, and then spring is neither compressed nor stretched initially, so that's why the initial spring potential energy is 0. Work non-conservative is 0 because there's no friction on the surface. So we get just the initial kinetic energy of the system is equal to final spring potential energy. And initial speed would be the speed of the system, 2.97 meters per second. We calculated it in the previous step. And you just have to rearrange the equation and solve for the compression of the spring. And I'm going to just show you how I get the unit meters here. Okay, so divide that by SI base unit of newtons kilogram meters per second squared, and then divide by meters again because newtons per meters is the SI unit of a spring constant, and then take the square root of whole thing. You will get 0.0667 meters or 6.67 centimeters.